Hi there. Let me introduce you to working with statistical procedures where you can deal with two samples where you're comparing means. So, is there a difference in how students do on the Geometry 1 final exam if Mr. Schaff was their teacher compared to if Ms. Hull was their teacher? Well, this time we're going to have two samples. We have a sample of students from my class. We have a sample of students from Ms. Hull's class, and I'm interested in seeing if there's a difference between what we believe the population mean Geometry 1 exam scores would be for these two teachers. So, mu sub s, this is the population mean Geometry 1 exam score for Mr. Schaff's students. Then similarly, we have mu sub h. This is the population mean Geometry 1 exam score for Ms. Hull's students. So the first thing you want to do is identify the parameters that you are interested in basing a test around. And the second thing, like any other statistical test then, is you want to create your null and alternative hypotheses. So what I'm interested in testing is the following relationship. Is there a difference between my true mean and Ms. Hull's true mean? So the alternative that I'm testing is Schaff's population mean different from Ms. Hull's? So the null hypothesis then would indicate that there is no difference, so those two means are the same. Now, when it comes to actually calculating the value, the p-value here, when we're doing this test, we need an actual number for the null hypothesis. So it's best to rearrange this by subtracting, let's say, the mean for Ms. Hull from both sides of this equation. So really what we're saying is the null hypothesis says that the actual difference between these two population means is 0. That's another way to write the null hypothesis, versus the alternative, where the difference between the two population means is not equal to 0. So this involves means, so we're going to run a t-test, and shockingly, because there are two samples, we're going to call this a two-sample t-test. Now, in terms of the conditions, we have randomness, independence, and normality. Now, I know you can read, but I'm going to read this with you. Are both samples random? We need two random samples, preferably two SRSs. What's interesting about this, though, is the situation which we just happen to be in here regarding Ms. Hull and my students. Each sample is of size 22. During the same class period of the day, first trimester, Ms. Hull and I both taught Geometry 1, 5th period, and we each had exactly the same number of students, 22. So it's reasonable to believe that students were randomly assigned to either Mr. Schaff's or Ms. Hull's class when their schedule was generated by the computer. So in this way, this scenario is like an experiment where subjects have been randomly assigned to two different treatments, the Schaff treatment or the Hull treatment. So there are many scenarios in which we have two treatment groups, and we're interested in considering the difference between the mean response from those two treatment groups. This is essentially what we're doing here. So it's important that randomness be a part of both samples. So independence. Are the samples independent from one another? In terms of independence, what's most important is that there's no connection between Ms. Hull's students and my students. So for instance, if all of the freshmen ended up in Mr. Schaff's Geometry 1 class and the sophomores and juniors and seniors all ended up in Ms. Hull's Geometry 1 class, then essentially those two classes would not be independent. They would be dependent in terms of the fact that one age ended up in one class and another age ended up in a different class. So I want to believe that there's really no relationship between those two classes. So in practice, you can also check this condition as we've checked this before. You can think about taking 10 times the sample size. So 10 times 22 is 220. So this would have to be less than or equal to the number of students who have taken geometry with Mr. Schaaf. Now, of course, I didn't have 220 or more students this year. I only had this one class of 22. So we are acting as if this group of 22 is representative, if you will, from the entire population of Geometry 1 students that I've been teaching. So same thing for Ms. Hull, 2 times 22, 220. Again, that would be less than or equal to the population of Ms. Hull's Geometry 1 students. So ultimately, in terms of these two conditions, you need two independent random samples. So both samples need to be random, and the samples need to be independent of one another. So in terms of normality, some of this will sound familiar. So now we're not just working with one sample, we're working with two samples. So if you combine the sample sizes, so here 22 plus 22 makes a total of 44. Is that large enough to believe that the sampling distribution is approximately normally distributed? So in our scenario here, just like we did with one sample t-tests, we're going to choose to compare to 30 in terms of being, quote, big enough. So our two sample sizes are 22 and 22. That's a total of 44. And certainly that's greater than 30. So in theory, the sampling distribution, so the sampling distribution will be the distribution of the difference between our two sample means, is approximately normal. However, bigger samples are always better. So there isn't anything really magical about 30. Bigger tends to be better in this case. And also, using the same sample size with each treatment group is also best. So having similar, if not exactly the same sample size with each sample, with, in this case, the two, quote, treatment groups, the closer those sample sizes are, the more accurate this test is when there happen to be deviations from the conditions. So that means this test is more robust if the two sample sizes are close together in size or are exactly the same. So just like before, though, if the combined sample size is small, say if it's less than 30, then again, we should verify that there are no outliers or any serious skewness. And certainly if we have very small samples, say 15 or less combined, then I want my two sample data distributions, I want them to look reasonably symmetric. I certainly don't want any outliers. So here, take a look. At the top of the second page then, here are the actual data from my class and from Ms. Hull's class. So if you haven't taken the time to do this already, take a moment and enter these data into list 1. So put Mr. Schaaf's class into list 1. Put Ms. Hull's class then into list 2. Pause the video and do that. I want to talk about what we see in the sample data, and then in the second video we'll actually do the test and complete the calculations. So if you haven't entered the data already, pause the video and then start playing it again, and we'll talk about what we see. So in terms of these two lists, again, I have my class in list 1, I have Ms. Hull's class in list 2. Even though the sample size combined exceeds 30, it's still important to graph the data and get an idea of what's really going on. So again, these are test scores, so a window from 0 to 100, I called it 105. I used a scale of 5. That's perfectly good enough. You can zoom 9 if you want to. I just want to be able to see the box and whisker plots. So if you press second y equals, I would want you to realize you can plot the two data sets simultaneously. So my exam scores are on list 1. I've specified a box and whisker plot where outliers are checked for. It's turned on. Same thing, plot 2 is on using Ms. Hull's data. Also a box and whisker plot. So graphing these simultaneously, understand my data do not show any outliers and they are reasonably symmetric. But Ms. Hull's data is strongly skewed to the left and there are also 2 outliers. So these are real data. It is what it is. Understand, even though we said that 44 is greater than 30, in the end, the result of this significance test really needs to be considered with a grain of salt, especially if you're going to use the result of this significance test to actually say something or make a conclusion or make a judgment, if you will, about the respective teaching abilities of these 2 teachers. In fact, the outliers need to be considered. Are these outliers that you actually want to keep in the data set? Is there some reason to believe that these students really aren't representative of the other students? I would offer that the outliers are what they are. They should remain in the test at this point, unless you have good reason to pull them out. But understand they will affect the t-score and they will affect the p-value that you are going to get when you do this analysis. So when there are outliers, the result of this analysis, you really do have to take with a grain of salt. You really do have to appreciate the effect of those outliers in the context of the question. So we are going to proceed with this test. We will, in the next video, do the actual calculations, and then we will interpret the result of this 2-sample t-test in context.